Okay, hi everyone. My name is Kenneth and I'm a first year student in the Bachelor's of Science in Education currently studying at the University of Malaya. So today we'll be discussing about the factors which affects the mechanism of enzyme action. So these factors are actually taken from the Form 4 syllabus, Chapter 5, Metabolism and Enzymes. Let me explain. These factors are quite easy, and if you understand it, you have no problem in gaining an A plus in your SPM biology. What have we learned previously? We learned about the structure and what is an enzyme. An enzyme is an organic catalyst that is mostly made up of proteins. Okay, the keyword is here, proteins, and is produced by living cell organisms. So what are proteins? Proteins can be denatured at extreme conditions. Okay, this is what we learned before, right? So same, and since enzyme is also a protein, it will be denatured at extreme conditions such as temperatures, extreme temperatures, pH, etc. But don't worry, we'll be learning this later. Okay, so what is the mechanism of enzyme action? It is the lock and key hypothesis. Okay, these substrates will enter the active site of enzyme, they bind together and form an enzyme substrate complex. And finally, the substrate has been converted into products and it left the enzyme. Okay, you can see from this animation, the substrate bind with the enzyme, and yeah, products are created, but it's not shown here, of course, in the animation. Students, be an enzyme, a catalyst for change. How? Being successful in life, make changes to yourself and to the people surrounding you, and you will be automatically an enzyme for change. So now let us discuss about the factors which affects the mechanism of enzyme action. Okay, there are four factors, which are temperature, pH, substrate concentration, and enzyme concentration. So what can you see from this graph of temperature? Okay, this is the first factor, which is temperature. From this graph, we will be analyzing the axis first. Okay, so this is the rate of reaction for the y-axis, and on the x-axis, what is it? The temperature. So what is portrayed on the curve? Okay, you can see the curve is constantly increasing. It reaches the peak here. However, after this peak, it is decreasing. Okay, what does this mean? This means that enzyme reaction, okay, rate of reaction is meant by the reaction of enzymes. Enzymatic reactions, it increases on this part here, okay, and then it reaches a peak, but suddenly it decreases after 37 degrees Celsius. So what happened actually? Okay, you can see from this animation. In the beginning, it gains kinetic energy and the enzymes and substrates are moving. Okay, but however, when it reaches the peak, nope, it reaches the peak is meant by the optimum temperature of 37 degrees Celsius, right? Okay, you can see it gains kinetic energy when temperature increase, and this is the optimum temperature for enzyme, and the enzyme bind with the substrate together. But however, if the temperature continue to elevate, what will happen? The enzyme will be denatured and they can't bind with the substrate. They can't bind with the substrate again. Okay, it's very vague, right? But don't worry, we'll explain this in further details later. So step one, what is happening? At a low temperature, the rate of reaction catalyzed by enzymes is low. Okay, you can see from this graph, the curve is still very low. Okay, so what happens when the temperature rises? The kinetic energy of the substrate molecules and enzymes increases. Okay, and what will happen next? This increases the frequency of effective collision between the substrate molecules and enzyme molecules. Remember what has been discussed in the lock and key hypothesis? The substrate will bind with the enzyme and form an enzyme substrate complex. So if the substrate molecules can bind with the enzyme molecules, it is an effective collision. Effective collision means it produces substrate, and it's a successful rate of a successful reaction. Okay, so what happens when the temperature increases? If the frequency of collision if the temperature increases, the frequency of effective collision increases. Okay, as well, the rate of reaction between the enzymes and substrate molecule increases too. Okay, with every rise in temperature of 10 degrees Celsius, okay, you can see with every rise in temperature 10 degrees, the rate of reaction will double. That's why the curve is so steep, because it is increasing in double speed. Okay, until it reaches the optimal temperature. So what do you mean by optimal temperature? It's 37 degrees, almost the same temperature as our human body. As you can see from this animation, at low temperature, are, you, are the particles moving faster or slower? It's moving slower, right? But if we increase temperature, how the particles are moving? Observe their speed. It's moving a little bit, at least a little bit faster. But oh wow, we increase the temperature even more, and what happened? You can see that the speed of the particles are increasing. Okay, that means the kinetic energy of these particles is increasing too. So if temperature increases, the kinetic energy increases, and the speed of particles increase. So what happened at optimal temperature? At the optimal temperature, the enzyme reaction is at its maximum. It's at its peak level. Okay, so the optimal temperature for enzyme reactions are the same as the temperature in human body, which is around 37 degrees Celsius. Okay, so after reaching the optimal temperature, any further increase in temperature will reduce the enzymatic activity rapidly until it stops at 60 degrees Celsius. So you can see why the curves touches the 0 point in 60 degrees Celsius. Is because the enzyme activity has stopped due to high temperature. Okay, so at this temperature, what will happen? The enzymes became denatured. Okay, and the chemical bonds, because of the enzymes, they are connected with chemical bonds. Okay, and the enzyme molecules will break, and they're unable to retain the 3D form and active sites of enzyme changes, and the substrate can't bind with the active site of enzymes anymore. Okay, what do you mean by this? Okay, you can see this is what is meant by denature. Before the denaturation of enzymes, you can see the substrate can bind successfully with the enzyme yet, because the active site is still in a good condition. But how about if the protein is denatured? No, sorry, is the how about if the enzyme is denatured? You can see the substrate, they can't bind with the enzyme anymore. It's because the active site of the enzyme has changes its shape. Okay, so okay, you can see this is the enzyme in the native state or active state, which means it haven't denatured yet. So in the natural form of enzyme, there are chemical bonds here. Can we draw the chemical bonds which hold the enzyme molecules together? And what will happen if the temperature is keep increasing? If the temperature keep increasing, you can see it breaks the chemical bonds here. Okay, it breaks the chemical bond, and then the enzyme molecules are separated far apart. And you can see if the enzyme molecules are separated, how about the shape of the active site? The shape of the active site is already altered, and as well as their 3D form of enzyme. Okay, so if the shape of the active site are altered, the shape are so important for the substrate to bind with. Can the substrate bind with the altered shape of the active site? Of course, no. So extreme temperature will affect enzymatic reaction in this way. Okay, so these are the most important points to remember. It is denatured as the chemical bonds break, okay, and it's unable to retain the three-dimensional form. Okay, it's here and it's here. Okay, remember these 2 points, it's very important. and active sites of enzyme changes, the substrate does not complement with the active sites. Okay. So now let us move on to the second factor, which is pH. So different enzymes, they have different optimum pH. Optimum pH means the standard pH level for the enzyme to remain in its active state. Okay, so for pepsin, they have its different optimum pH than salivary amylase and trypsin. Okay, so if the same concept as the temperature, if the enzyme is immersed in an extreme p a solution with extreme pH, what will happen? The enzyme will be denatured. Okay, it's the same concept here. Okay, it's a normal enzyme, it will be denatured. The chemical bonds which hold the enzyme breaks. You can see, so the enzyme become far apart. So what happened in optimal pH? In optimal pH, most enzymes are um, most active in the range of pH between 6 and 8. Okay, for example, salivary amylase, it is the most active in pH 6.8. How about pepsin? The optimal pH for pepsin is 1.5 and 2.5, while trypsin, it is more active in an alkaline medium and pH for around 8.5. So what will happen in extreme pH? The change in pH value changes the charge on the active site, okay, and the substrate surface. So both of them, both of the active sites on the substrate and the enzymes undergo changes. As a result, of course, the enzyme substrate complex cannot be formed. There is a decrease in the rate of reaction. The extreme changes in the pH value will break the structural chemistry bond and change the active site of enzymes. So when the pH reaches its optimum value, okay, it is a good thing where the charge on the active site will be restored and the enzyme will return into its normal state. Okay, so what do you mean by these sentences? It sounds very unclear, right? Let me explain to you in this diagram. During low pH, what will happen? During low pH means an acidic condition. Acidic condition, they have, for example, these hydrogen ions, they will bind with the ions in the enzyme. Okay, for example, these enzymes, the active site, they initially they have COO minus ions, right? But how if in low pH there are other ions which interferes with the ions in the active site? And what will happen? This active site is no longer usable because the ions in the enzyme active site has changed, right? So it cannot form an enzyme substrate complex. Okay, it is the same concept on during high pH. What will happen? Okay, in high pH level, the ions in the enzyme active site, they will donate hydrogen ions out to the solution. Okay, so what can we see from these two diagrams is the change of ions on the active site in extreme pH solution. Okay, if the active site undergo changes in ion, therefore the substrate cannot bind with the active sites of enzymes anymore. They cannot form enzyme substrate complex, and the charges on active site will be changed as well. Okay. So now let us move on to the third factor, which is the substrate concentration. So what can you see from this graph? You can see the substrate concentration is increasing until it reaches its maximum level. Maximum level means that there are too many substrates, but the enzymes are limited. So this is what is meant by substrate concentration. So what will happen at its maximum level? The rate of reaction is constant, you can see, because the substrate is too much and there is insufficient enzyme to bond with the substrate. Okay, so you can see if the concentration of enzymes is fixed, okay, and we make changes on the substrate concentration itself by increasing it, the rate of reaction increase, and as well the products will increase too. When the substrate concentration increases, what will happen? The frequency of effective collision between the substrate and the enzyme molecules, they will increase, as well as the rate of reaction. However, it will increase until the rate of reaction reaches the maximum value. After this, no more, it will remain constant. At the maximum level, what will happen? The concentration of enzymes becomes a limiting factor. Okay, because we keep increasing the substrate concentration. There are more substrates. However, if there are more substrates, where are the enzymes? How can they bind with the increasing number of substrates, right? Because the enzymes are simply just not enough. Therefore, the rate of reaction can only increase if we increase the enzyme concentration. And all active sites in the enzyme are bind with substrate and are involved in the rate of reaction. Okay? So what do you mean? You can see initially during low, okay, S is meant by substrate concentration, yeah. During low substrate concentration, you can see there are a few substrates and sufficient number of enzymes to bind with it. How about it's a medium substrate? You can see in a medium substrate concentration, there are a little bit of enzyme with some substrates here. So the number of enzymes is still sufficient for the substrate to bind with it. But next, this is more important. How about high concentration of substrate? You can see there are lots of substrate here. You can see out of this round shaped structure are substrates. But how can we do with these enzymes? There are only like 1, 2, 3 enzymes, but there are more substrates. So the number of enzymes are insufficient to bind with the increasing concentration of substrate. Therefore, you can see the rate of reaction here, represented by this curve, remain constant. Okay? So now, let us move on to the last factor, which is enzyme concentration. So from this graph, what is the difference between the enzyme concentration and the substrate concentration graph? The difference is in the x-axis. You can see enzyme concentration, but the curve is still the same. Okay, so if we increase the enzyme concentration, if there is sufficient substrate, then the rate of reaction will increase. This is the first part. But how if the number of substrate is insufficient for the increasing number of enzyme to bind with it? Therefore, the rate of reaction will remain constant here. Okay, so what do I mean actually? When the concentration of enzyme increases, the rate of enzymatic reaction will increase. Why? Because more enzyme means there are more active sites, right? Which are ready to catalyze a reaction. So if the concentration of an enzyme in one reaction is doubled, the amount of substrate converted to products per unit of time is also doubled, with the condition that there is an excess supply of substrate. What does this mean? If we increase the enzyme concentration into double, okay, for example, one enzyme to two enzyme, and then the amount of substrate converted to the products per unit of time will be doubled too, right? For example, if we increase the number of enzymes to two enzymes and there are two substrates, then both of them can bind with the same time. It saves the half amount of time. Okay, it is the concept like this. At the maximum rate, however, the concentration of the substrate becomes the limiting factor, and the rate of reaction can only be increased by adding more substrate into it. Okay, it is the same concept with substrate concentration, just we change the role of concentration here. Okay, because this is enzyme concentration. So if we increase the enzyme concentration, what will happen? The concentration of the substrate will not be enough. How about we do it in the opposite? If we increase the substrate concentration, what will happen? Of course, the concentration of enzyme will not be enough. Okay, so both of them, the substrate concentration and the enzyme concentration, are the same concept. Okay. Okay. I illustrate the diagram here already. The yellow the yellow structure is represented by enzymes, while this is the blue structure is represented by substrate. Okay, so when the substrate it binds with the enzyme, it catalyzes a reaction and the rate of reaction increase, right? But you can see here the enzymes are just a few, but there are more substrates. So there's no problem in initializing a reaction here. Okay, what about we increase the concentration, the number of enzymes? You can see there are more enzymes here, and more substrate can bind with the enzymes, right? Okay, how about the third diagram? You can see the number of enzymes are increasing. And how about the substrate? It is not enough, right? There are only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 10 substrates. But there are more enzymes than that. So you can see there's not enough substrate to bind with the enzyme. Therefore, the rate of reaction is in a flat line. Okay, you can see from the graph, it's a horizontal flat line. So these are the references we use in the presentation. If you have time, you want to have a further knowledge on this, you can have a look. Okay, and remember, success is not final. Failure is not a fatal moment for you. Okay, don't be afraid if you failed, because the only winning factors which determine you and others is the courage to continue your effort that counts. And that's all from me. Thank you for listening to my video. I hope everyone stays safe and stay focused on your studies. Bye bye and thank you.